For lab activity 5, Earth's magnetic field, we have to start thinking about what's taking place inside the Earth. We're going to be studying terms like magnetic declination, which is where the Earth's magnetic field is going to locate a magnetic pole, which is different than the Earth's geographic pole. So that means we need to pay attention to what's going on inside the Earth. So the Earth's structure is very relevant. Here we can find that the Earth's crust is the outermost, the thinnest layer of rock, of solid rock, and beneath it is the mantle. We have an upper mantle, we have a lower mantle, we have a liquid outer core, we have a solid inner core. And by now you might be saying, well, how do we know this? Well, here's how we know it. We know it because seismologists have been able to study how waves, earthquakes, primary waves and secondary waves of an earthquake. Here's the earthquake, the epicenter, the location of the earthquake itself. Earthquakes give us an indication as to what's taking place beneath the Earth's surface. So we can actually view it with technology, and we don't actually have to be there. So this simulation shows the motion of primary and secondary waves generated by a single earthquake. The waves spread through the planet in a series of expanding spheres. Some of the wave energy reflects off the boundary between the mantle and the core. Right? You'll see this reflection here. Scientists deduce that the structure of the Earth's interior and how waves move through it by analyzing thousands of earthquakes recorded at the Earth's surface. Examine how the waves change as they encounter different, in this case here, different layers of the Earth's interior. Identify areas on the surface that do not receive any waves. These areas are in the shadow zone of the simulated earthquake. So here's another animation that I can show you. And this is going to show us the layers of the Earth. That the Earth is made of concentric layers of rock with a rich core of iron-rich metal, right? The inner core. Notice that this is just another earthquake here. And we can view this. So the Earth is made of these layers. And how do we know this? Well, we study these seismic waves, right? Earthquakes. And they give us this visual indication of what's taking place. So now I can even further divide the layers I mentioned before. We can say the crust is the solid upper rock, where we have the lithosphere is the crust and the upper mantle, the solid parts of the Earth. Lithos means rock. Then we have this layer called the asthenosphere. It's kind of a plastic, kind of a ductile layer that allows for plates to move on the Earth's surface. We have an upper mantle, we have a lower mantle, we have an outer core, right, a liquid outer core, and we have a solid inner core. So when we go back and look at this picture, we can start making sense as to what's taking place inside the Earth that's going to affect our ability to use a compass in class. So let's talk about what is magnetism. We're going to use a compass. A compass is driven by magnetism. Well, magnets exert forces. Magnets exert forces within a field that cannot be seen, but they can be felt by objects that have iron within them. Magnets have two opposite poles, and these are magnetic poles, the North Pole and the South Pole, just like the Earth. The Earth behaves similar to that of a bar magnet. Notice, here's a picture, here's a picture of a magnet. If I break it, it continues to be aligned with its magnetic fields and its magnetic poles, This is the space surrounding a magnet that it can exert a force. And that's the key part of magnets, is that they exert a force in surrounding space. And if I put a compass at different locations within that magnetic field, you'll see that they will align themselves very specifically. So opposite poles attract. Magnetic north and south poles attract toward one another, while like poles repel, right? North-north is going to repel and the south-south are going to repel. Attraction and repulsion are directions in which the forces act. The Earth has a magnetic field, just like each of these magnets. The larger the magnet, or the magnetic field, the larger the magnet, the larger the magnetic field. So the Earth has a really large magnetic field. It's just not that powerful. So here's a picture of what we call the Earth's magnetic field, the magnetosphere. And the magnetosphere is the area and space around the Earth that is controlled by the Earth's magnetic field. The Earth's environment extends all the way from the Sun to the Earth and beyond. It is not simply an empty wasteland of space. Instead, near-Earth space is full of streaming particles of electromagnetic radiation in constantly changing electromagnetic fields. Here's a picture of what our magnetic field looks like as the solar wind comes kind of streaming at us and towards us. All of these make up our magnetosphere. It is important to learn as much about the space around the Earth as we can. The magnetosphere helps protect our Earth from the danger of the Sun's solar wind. Before we watch a quick video on the Earth's magnetic field, our magnetosphere extends out 10 Earth radii. one Earth radius is 7,900 miles, or 12,640 kilometers. So we'll be able to calculate how large it actually is. So here we can watch the beginning part of this video.
We have a picture of the Earth's magnetic field. We're going to be able to view this from zooming out and taking a look at our place in space relative to the sun. It's constantly streaming charged particles towards the Earth. You'll find that those particles get deflected, those charged particles get deflected from the Earth's magnetic field, and they find themselves heading to the poles. And we see this result in the form of auroras, which we find in the northern hemisphere, called the aurora borealis.
So at this point, we should be asking the question, well, how does the Earth's magnetic field, how is it generated? And I want you to see that we're focusing on the inner and the outer core, that the inner core is a solid iron piece, solid sphere of iron, and the outer core is liquid. And this liquid outer core is having these convection currents that are moving charged particles. So there's no simple explanation. I'm going to give you the most accepted and kind of simplest form. You've got the solid metallic inner core central to the Earth. Convection drives the liquid outer core and circulates relative to the Earth's magnetic field. The Earth resembles an electromagnet, where one gets the same effect by moving electric current around a metallic interior. So here I can kind of show you this by this simple electromagnet. If I hook up a battery and a switch and coil, and I wrap these coils around here, and I run electric current around this iron nail, I can create a magnet, this nail, and we can demonstrate this in class, a simple electromagnet. This actually becomes a magnetic north, and this becomes a magnetic south end. So the Earth has a magnetic field around it because it has these charged particles moving around a solid iron core, just like that of an electromagnet. So we're going to use a compass to navigate on the Earth's surface. That a compass is simply a piece of iron that aligns itself within the Earth's magnetic field. It simply behaves because of forces acting on it. So the Earth's geographic south is located near its north pole, magnetic north pole, and the geographic north pole is located near the south magnetic pole. Now that should kind of throw you for a loop for a second, but think of it this way. Magnetic field lines are always drawn from magnetic north to magnetic south. And so if I look at the magnetic north end of this magnet here, magnetic field lines are drawn from the geographic south pole towards the north pole. So what geographic north is, it's actually south magnetic pole. And a compass will help make sense of that. When we hold a compass in our hand, we know that the compass end, right, the red end is the north pole. It's going to attract to the south pole, so it's going to point this direction. So a compass is going to tell us where the magnetic poles are located. And not only is the magnetic pole, it's not stationary, it's actually moving at this current time. The poles actually switch, and these are called magnetic reversals. And these happen or occur about every 500,000 years of a periodicity on average. So magnetic poles are actually moving. I mean, we can look here from 1900 to 2000 in 100 years, it's actually moved quite a significant distance. And so we can use a compass, and it's going to align itself, and it's going to help us make sense of what's going on within the Earth's magnetic field. And this is what we call magnetic declination. Declination is the result of true geographic north not being in the same location as magnetic north. So the compass will naturally point to the magnetic south pole, which is near true or geographic north pole. This takes a simple movement of the adjustable ring to orient the compass. And because it's kind of hard to describe using this compass, we're going to actually do this in class. And we'll have a chance to do this. We're going to use the Earth's magnetic field to use a compass to navigate on Deerfield campus. And we'll get a chance to practice that. And last but never least, the magnetic declination is provided at the bottom of topographic maps. So most locations are going to have some declination. It's essentially the difference between where true north is, or geographic north, and where the compass needle is pointing. We have to compensate that, and that's your magnetic declination. It's the difference between true north and the magnetic pole that we're looking at. So there you have it.